Hey year eights, welcome to week 4 of term 2, and it's my turn to present some mathematics to you this week. Alright, so what I've got lined up for you is on the menu we have a bit of Pythagoras Theorem, possibly one of the most well-known theorems that we work with in mathematics. It's my privilege to present that and bring that to you this week. We're going to spend a couple of days having some fun with that. Pythagoras Theorem, a little spoiler, it's about right-angled triangles and the sides of right-angled triangles. It's a really fantastic, cool relationship between the lengths of the sides of a right-angled triangle. So that's where it all starts. And then, so we'll have a couple of days looking at that and playing around with that. That's Monday, Tuesday. Thursday is going to be a revision lesson because on Friday we've got a little test for you, a little unit test on measurement, because Pythagoras is the last little piece of work for us in this unit that we're covering here on measurement. So let's go. Righto, let's get into this Pythagoras business then. So what I'm going to get you to do during the course of this lesson is, because sitting there and just listening to me carry on is not really going to work. You're going to just fall asleep. So I'm going to get you to do stuff, all right? So when I call out pause, do, play, pause, do, play, what I'm asking you to do is a 3-point exercise. One is pause. Pause the video and do, next part, do what I ask you to do, and then hit play again, right? So I'm going to ask you to do pause, do, play, except I'm going to call it, I'm just going to say PDP. Right? I'm going to shout out PDP, and that means you have to pause. And you have to do, when you pause, you don't just pause and go for a kick of the footy. You pause and do what it is that I've asked you to do. So here's the first example. What I want you to do is pause and draw a 5-centimeter horizontal line. All right, so get your ruler out. I've got a little grid here that goes for 5 centimeters. So I'm in good shape here just to draw a 5, except you need to, all right, so make it low enough down on your page so that you can draw, so there's enough room to go vertically 5 centimeters, if you get what I mean. So I'm going to go 5 centimeters, 1, 2, 3, 4, is that 5 there? Okay, so 1, 2, 3, 4, 5 centimeters, vertical, horizontal line. Do that, then I want you to construct a square on it. All right, so 5 centimeter line, then I want you to construct, so you pull that down, that's 5 centimeters, but importantly, I'm going to want you to construct a square on it. That means you use that side as one of the sides in a 5 centimeter square. All right, so you go to work, I'm going to finish my square off. Pause, do, play, PDP. Okay, so I hope you have a really nice looking square like I do, 5 centimeters by 5 centimeters. Right, what we're going to do now is find the area of this square. Right, so let's do that together. Area equals, we've just done area, so we know that we've just got to multiply these sides together, right, to get 5 times 5, although we mathematicians have shortcuts for everything. So we don't write 5 times 5, we write 5, or a shorter way is 5 to the power of 2. 5 to the power of 2. But what do we call that to the power of 2? We say something else, don't we? What do we say? We say 5 squared, don't we? That power of 2, 5 squared. Hold on a second. 5 squared. Why do we call it 5 squared? Well, this is why we call it 5 squared, because when we take the area of a square, well, we multiply 5 by 5, or 3 by 3, or 10 by 10, or x by x, and we call it x squared, or 5 squared, or 3 squared. So that's why we call that little 2 power there squared. Right? It helps us with areas of squares. 25 centimeters squared is our area there. Great. Little intro, little history about why we call that thing squared. Important, because we're going to build on that. Okay, next thing I'm going to ask you to do in this pause, do, play little scenario is that I'm going to ask you to do, I'm going to ask you to draw a triangle now, right? A right angled triangle. So let's be really clear on what I need you to do here. So I need you to draw a right angled triangle. So what I want you to do, hopefully you've got grid squares like me, it makes it life really easy. I'm going to get my ruler out in a second when we'll do this together. I'm just going to draw a sketch of what I want you to do. I want you to draw a right angled triangle so that it looks something like this, just a straight up right angle triangle. Now, a right angle triangle has a 90-degree angle in it. Okay, so that's why we should use a vertical and a horizontal. It's just the easiest way to go. I want you to draw that triangle so that there's enough room around it to draw squares on each of the sides, right? So like this. Draw a square on that one. You're going to draw a square on this. This is the biggest side here. It's called the hypotenuse. All right, I'm going to chuck some language at you. So here you go, hypotenuse. I'm going to say that word heaps during this screencast. The hypotenuse is the longest side on a right angle triangle. So that needs the biggest square on it, obviously, because it's the biggest square. All right, so I want you to have enough room to draw squares on each of your sides. Right, so in a moment, I'm going to ask you to go and do this. So draw this triangle. I don't mind what lengths these are, but just make the triangle small enough so that you can draw squares on each of the sides, and you're not going to bump into other things on your page or go off your page or anything crazy like that. Okay, so I'm going to get you to, in a moment, pause. I'm going to get you to PDP, and what I'm getting you to do is just draw this triangle here, this blue triangle. Then we'll just come back and check on how things are going. All right, PDP, off you go. Okay, so I hope you've got a nice little right angle triangle like that. Let's just check it out. I want you to label the sides as well. A, B, and C. Very importantly, C has to be on the, what's it called? This longest side here. Starts with H. Well done, the hypotenuse. Let's write that out again. Hypotenuse. I'm just going to keep writing that down. Okay, that's the hypotenuse. So C is that length. A and B are the two shorter sides. And I don't really mind which side, but let's just do all the same thing. So if you've got a little vertical like this, call it A. If you've got a horizontal little like this, call it B, but make sure C is the hypotenuse. Okay, so that's what I want you to do in a moment. The other thing I want you to do is I want you to get your ruler out, and whatever that length there is, I want you to repeat that length across the other three sides to make a square that has that length A, whatever it is for you, 3 centimeters, 2 centimeters, whatever it is, so that length is all the way around. It's a square, and I want you to do that on each of your sides. So you've got squares sort of protruding, growing from each of the sides of your right-angled triangle. Okay, pause, do play. Off you go. Okay, you guys having fun with this? I hope so. I certainly am. Righto, so here we go. Hopefully your triangle now has sprouted these squares and looks a little bit like this. Remember, this side here is A, and this side's B, and this side, the hypotenuse, is C. Righto, so this guy here, right, let's look at this green square, the smallest of our areas. What is its area? All right, so what is the area of this green square? So what we've worked out is, and what you know, is that for a square, you've just got to square the side, right, the side. So if it's a 5 centimeter square, then you square the 5. Why is it called squared? Why is it called 5 squared? Because it creates a square. Then you get 25. If it's 3, if you had a little 3 here and you had a square going like this, and that was 3 and that was all the same length, you'd go, oh, I know the area, it's 3 squared, it's 9, righto. But if we change the 3 to an A, well, it's the same idea. We square the A. So the area here of this green square, area is A squared. So I'm going to write the area right there in the middle of that square. Let's go down here to this pink ready kind of square down here. It's got a length of B, and it's a square, so its area is, say it, right, B squared. Very good, excellent work. Okay, and similarly our square that sprouts off the hypotenuse there has a length of C, so its area is C squared. Okay, just right, so that picture there, let's have a look at it, because we're getting really close now to the punchline, right? To the exciting moment where we see what the relationship is between these three sides. We've set it all up. We're ready to go. We're just on the brink. So just remember, A and B are the smaller sides. C is the longer side. We're going to do a couple of little visuals now just to see what the relationship is between these three sides and the squares of those three sides. Okay. Okay, so let's have a little look at. I've recreated this little situation here that we had on our workbooks, and all right, can you see here? I've got this side here is A, and this side here is B, and this side here is C. So this is my A squared area here. This little patchwork of colours, That's my b squared in there. I'm just going to little arrow in there to the b squared. And this area here is c squared. Now look at what we're going to do. I'm going to have a little play around here. I'm going to drag some of these little sections across into the c squared. Let's see what happens. I'll just take this guy over here. I reckon he belongs there. So we're going to go around the edges of my c squared square and just fill in these gaps. See if he goes up there nicely. I think he will. Yep, there you go. Thank you. So b squared has been moved, right? It's still b squared. The area up here is still b squared. All right, those four still sum to b squared. And this a squared, he goes as a whole unit. And oh, look at that. Slots right in the middle there. You beauty. Okay, so beautifully, perfectly slots in a squared and b squared. You can see the a squared is that yellow in the middle. The b squared is that patchwork of colours around the outside. Together, they add up to c squared. That there is Pythagoras' theorem. A squared plus b squared equals c squared. Let's have another look at another kind of way that this can be demonstrated, and it's here in this little YouTube clip that's been made. And so what you'll see in a moment when I start this thing up is you'll see at the moment you see a similar scenario to what I just had. Let me just make this screen big. There it is. Okay, so you've got at the moment you've got the squares that are sort of protruding from each of the sides. You can see the hypotenuse at the moment is white, and the other two squares, well, they're blue, but they're full of blue liquid, right? And what's going to happen in a moment is this wheel's going to be turned the other way around, and that liquid is going to pour into the vacant hypotenuse square. That's c squared, right? So vacant, it's empty at the moment. And what we're going to see, well, let's play it and let's see what we see. What do you think we're going to get out of this? So this lady now is going to spin that wheel. Off she goes. There we go. And look at that blue liquid now. That's pouring out of those two smaller squares. And it's filling up the hypotenuse squared. And have a look at it. And the b squared is getting closer and it's almost empty. It's out. It's out. And we've got c squared is full. And the a and the b squared are empty. And we're going to tip it back the other way. Yeah, let's have another watch. Let's keep watching here. So now the c squared is emptying, and the a squared, the smaller squared, and the b squared are now full. How good is that, right? So that's a nice little demo, isn't it? Okay, how are we going here? This is pretty exciting. Now we're going to try and wrap this up a little bit. Here we go. So I've now got back to our a squared, b squared, and c squared, and I've written out here Pythagoras' theorem, because this is what it is. Pythagoras' theorem is, drum roll, a squared, smaller squared, plus the middle size square, the two of those, when you saw it done, you saw this b squared was all chunked up, but it fit around the corner of c squared, and you've chucked a squared in, it was perfectly matched up, and then you saw that wheel that was turned around. So a squared and b squared, those areas, they sum to c squared. All right, this is a really powerful result, because what it meant was that we could now measure, if we know two sides of a right angle triangle, we know what the third is going to be, because this always works. Bit like the circle and the diameter. Wow, we got 3 and a bit diameters that go around this circle. That's fantastic. Doesn't matter what size the circle is, it's always going to be the case. So that meant that we had this fantastic result, powerful as, because now we know the weight, now we know how far to get around a circle. It's just pi times diameter. So same sort of thing here. We're standing on the shoulders of giants of our past who have come up with these amazing things. So Pythagoras, or whoever it was who came up with this, this is what we got. A squared plus b squared equals c squared. This sort of stuff took centuries, decades to come up with, and we're just sort of throwing it into a 15-minute video. But I really hope you feel the enormity of this theorem and how powerful it is. Okay, so here it is. A squared plus b squared equals c squared. Now, what does that mean? So in words here, what I've written is, okay, you can see here in words, I've just, oh, hang on, what am I doing there? I'm just written out what it actually means, that a squared plus b squared, that means the sum of the squares of the shortest sides, right, these shortest sides, a and b, equals the square on the longest side, which is called the hypotenuse. So the sums of the squares on the shortest two sides, a squared plus b squared, equals the square on the longest side, the hypotenuse. in a formula in terms of algebra, it's a squared plus b squared equals c squared. Okay, let's test this thing out. Let's put it to work. What I want you to do, I'm going to get you to pause, do play again in a second, and this is what I'm going to get you to do. Very specifically, I'd like you to draw a triangle that has a 3 centimeter vertical. 1, 2, 3. I'm going to do this properly with a ruler in a second. I'm just showing you what I want you to do. So that'll be 3 centimeters. I then want you to take your ruler and go 1, 2, 3, 4, and please don't do it freehand like I am now. That's lazy. It's not good enough. And in this particular exercise, it just won't do. So if you're not going to do it properly, don't do it. Just but do it. So do it properly. So 3 and 4. Remember, this is a little right angle in here. And I just want you to draw those two measurements in, and then I want you to take your ruler and I want you to see what this length is. All right, I want you to measure it. I want you to measure it, and I want you to put down whatever you get into that slot there. Okay, pause, do, and then come back. Press play again and come back to us. Okay, so that's your nice neat triangle. Hopefully 3 centimeters here, 4 centimeters along the horizontal, and then this dotted line. You measure it, and what did you get? What did you get? Let's ask Pythagoras what we should get, because it's a right angle triangle, so it has to obey the Pythagoras theorem, doesn't it? So what is Pythagoras theorem again? I'm going to write it in this way. C squared equals a squared plus b squared. I've just turned the formula around, right, from this pretty little formula up here to c squared equals a squared plus b squared. Same thing, righto. Now, I don't know what the length of that c is. That's my c there. Remember, c squared, c is the hypotenuse. Right, the a and the b, they're the other two sides. So the a in this case, I'm going to say is 3. It doesn't really matter whether which is a and which is b. But at the moment, a is our smallest, b is our next biggest, and c is our biggest. So we're just going in alphabetical order like that. 3 squared plus 4 squared, right? That's what c squared equals. I've got to add the squares. What does it say? The sum of the squares of the shortest sides, right? The sum of the squares. The sum of the squares. 9 plus 16. If I drew a square on this 3, right? If I drew a square there, it would be 9 centimeters squared. If I drew a square on this guy here, it would be 4 by 4, 16 centimeters squared. And we could put that 9 and that 16, and we could plonk it on this square here. That was what you just saw. That was the proof of Pythagoras, and that's what we're using right here. So 9 plus 16, that's 25. So what that means is that this square on C is 25 centimeters squared. So therefore, C, the side, if this area is 25, if this big old square here has an area of 25, which I know it must be because this is 9 and this is 16, and the sum of them give me this big square here. If that's 25, what's one side? What's this side here? The hypotenuse, that's that side there. That's what I want. Well, it's the square root of 25, isn't it? The square root of 25. And you guys know that the square root of 25 is 5. So, did you get 5? I reckon you would have. If you drew this really carefully and accurately, I reckon you'll have been very, very close to 5 centimeters there with your hypotenuse. So C is equal to 5 centimeters by Pythagoras' theorem. Wow, this is fantastic. Okay, so we have this 3, 4, I'll put 5 in here. We have this 3, 4, 5 centimeter right angle triangle. And I want to introduce another word to you now, or another term to you. 3, 4, and 5, because they form a right angle triangle, they're called what we call a Pythagorean triple. All right, so 3, 4, and 5 are therefore a Pythagorean, that's a big old word, isn't it? Pythagorean triple. All right, that's going in another color. Hang on a second. All right, you guys are doing well here. 3, 4, and 5 are therefore a Pythagorean triple. Why? Because you can make a right angle triangle out of them. How do we know? Because 3 squared plus 4 squared equals 5 squared. So let's test these. 6, 8, 10. Is that a Pythagorean triple? Well, let's test it. There's only one way to find out. We have to do, this is the test, right? This is the test. Is 6 squared plus 8 squared equal to 10 squared? right? Yes or no? The answer is yes or it's no. 6 squared, 36. 8 squared, 64. Is that equal to 100, right? This is a question mark. Is it equal to that? Is it equal to that? 36 plus 64, well, I reckon that's 100, isn't it? So 100 equals 100. Yes, it is. So we have, therefore, 6, 8, 10 are a Pythagorean triple. We can make a right angle triangle out of these three numbers. Centimeters, meters, kilometers, whatever. Let's test 4, 5, 9. Are the numbers 4, 5, 9 a Pythagorean triple? Let's do it. Test. All right, is 4 squared plus 5 squared equal to 9 squared? Let's test it out. 4 squared, 16. 5 squared, 25. Is that equal to 9 squared, 81? I don't reckon it is. 16 plus 25, that's only 41. 41's not equal to 81. This is not a Pythagorean triple. Not a Pythagorean triple. What does that mean? Well, it means we can't make a right angle triangle out of the numbers 4, 5, and 9. That's impossible. Righto. So I want you to now do a PDP for these numbers here. R4, 6, and 8, a Pythagorean triple. R3, 4, and 5, a Pythagorean triple. I want you to test them both, and then I want you to press play and come back. I'll have the solutions up by then, and you can check your work. Okay, pause. Right, how'd you go? I got no for 4, 6, 8, because 16 plus 36, I got 52 for the sums of the two smaller sides squared, and 64 for the largest, the hypotenuse squared. They're not equal. That is not a Pythagorean triple right there. Can't make a right angle triangle out of it. 3, 4, 5, however, 3 squared plus 4 squared. They're the smaller sides. 9 plus 16, 25. Square the larger side, square the hypotenuse, get the same number. 25 equals 25. This is a Pythagorean triple, ladies and gentlemen. Okay, got one more example for you before we head into the exercises. Okay, how about I do the first one, and then you do the second one as a pause, do, play. Are these triangles right angled? See, this is just a regular triangle here. I don't know, there's no right angle in there. I've got to test it. I'm going to use Pythagoras because I know I've got something up my sleeve now. A right angle triangle, the sums of the squares on the smaller two sides have to equal the square on the larger side. I know this, right? So I'm going to test. Here's my test. Same as for the Pythagorean triple. It's basically saying is 4, 7, 9 a Pythagorean triple. Test 4 squared plus 7 squared. Is it equal to 9 squared? Let's go. 16. 49. Is that equal to 9 9s or 81? Is 16 plus 49 equal to 81? 16 plus 49, that's 65. That sure is not equal to 81. That's a no. So that means that this triangle here, sure, it's a triangle, no problem at all, but there's no right angle in it. Okay, do a PDP on this question here, 6, 8, 10, and then come back and let's check our answers. All right, here we go. Test. 6 is 6 squared plus 8 squared equal to 10 squared. I've got a feeling it is. 36 plus 64 equal to 100. Yes, indeed it is. Yes. So what does that mean? What does that mean? It means that this is a right angle triangle. Where's the right angle? It's got to be opposite the longest side, hasn't it? This is the hypotenuse here, so it's got to be in there. All right, remember what this guy's called here? Hypotenuse. That's him. Okay, you guys have been great. Now it's time to go and do, what is it? Exercise, is that 4K up there? Exercise 4K. So go to the work requirements and get 4K done and have heaps of fun with it. I'll see you soon.